Alright, so the sample exam has come out, as you might have seen. So what I'm going to do today is have a go at it. Fresh, I haven't had a look through it yet. I've uh, I've seen maybe one or two questions around, but I haven't attempted them yet. So I'll give myself a bit of a time limit. Um, I'm probably gonna be done before the time limit, and I'm not really gonna go back and try and double check my work and things like that. This is basically just a preliminary. When I'm looking at it, what would I answer? What do I think the marks would be for the sake of the short answer ones? So obviously, if I took a deep dive into the questions, I might have a more thorough marking guide or something like that. But this is just going to be if I was in the exam right now and I was somewhat speeding through it. Here's what I would do. So I've got the question answer book here. I've got my data book here, and I have a calculator set up on the side that hopefully you can see for the quantitative questions. So we've got 15 minutes reading time. Now for the reading time, my usual strategy is that I look through the multiple choice ones, and I'm going to have a go at the qualitative ones. I'm not going to have a go at the quantitative ones because I might not remember exactly what number I get. Now, rather than doing the full 15 minutes of reading time and then just going back and circling them, which is what I would normally do if I was sitting the exam, I'm just going to circle them as we go through because you probably don't want to watch me spend 5 minutes going back and circling the answers that I'd come up with during reading time. So I'm just going to circle them as we go through, and then I'll go back and do the rest of the multiple choice once I start writing time. Alright, so I'm just going to circle them on the exam as well because I can't be bothered to have a separate multiple choice answer sheet, and that would be really annoying. So we've got 30 questions for 30 marks for the multiple choice. That's just the same as always, and we've got 90 marks for section B, same as always. We'll see if the structure is any different, and I'll make some commentary as I go through on the overall structure of the exam and things like that. Alright, so I'll start my 15 minutes. Okay, having a look at the instructions. That's all basically the same. Alright, compared with ethanol produced from coal, the ethanol produced from sugarcane has higher energy content. That is not correct. It's going to be generally the biofuels are going to be lower in terms of energy content. They both have low efficiencies because combustion is just low efficiency. Can be classified as a biofuel. That's it. That seems like the slam dunk answer. If you don't know that bioethanol is a biofuel, probably review chapter 1. Cannot be used to generate electrical energy. That's not right. You can just burn it in a generator. Produces no greenhouse gases when it burns. That's wrong. Remember that it still makes greenhouse gases. You could debate whether it's carbon neutral or not, in the sense that the creation of it and the burning of it has no net release of carbon dioxide, but it still releases the greenhouse gases. Something like this is just always referring to if you wrote up the combustion equation, does it have carbon dioxide as a product, or water, or whatever? And yes, it does. So, can be classified as a biofuel. Again, that's me giving commentary on it. You can probably finish it faster than me in that sense. In humans, the oxidation of which chemical is the primary carbohydrate energy source? So we've got amylopectin, amylose, glucose, or glycerol. If you don't know what amylose or amylopectin are, you might be able to come down here and you can say, it's amylose and amylopectin. We've got starch here. So are they the primary carbohydrate energy source? You can break them down when you eat a plant, but really, what do we actually break them down into? We break them down into glucose. Now, glycerol is not a carbohydrate, so that's just out of the question in the first place. These other two can be used, and they can be broken down into glucose. Cellulose cannot, but those two are just broken down into glucose anyway. So, alright, a box of rolled oats provides the following information. Alright, which component of this breakfast cereal will contribute the least energy when one serve is completely digested? Okay, so we've got serving size of 40 grams. So basically, with the serving size being 40 grams, and this is the average quantity per 100 grams, whatever energy value we get out we're going to need to multiply by 0.4 because the serving size is only 40% of that average quantity. So that's a trick that I reckon they're going to play that trick in one of those answers there. Now let's find our foods. There they are. 37 for fats and oils, 17 for protein, 16 for carbohydrates. So they've got carbohydrate because it has an energy content of only 16 kilojoules per gram. It does have an energy content of 16 kilojoules per gram. Let's have a look at what we can actually do with that, whether it's the least or not. So the carbohydrate is going to be 55.6. I'm not quite sure why I started with D. So times 16, or we could think about it as 55.6 is the amount per 100 grams. I should be doing this on the calculator here. So 55.6, and I'm going to multiply by 0.4 because that's how much there is per 40 grams. So 22.24 grams per serving. I said I wasn't going to do any quantitative ones, and yet here I am doing them. Anyway, I'll finish this one and then try not to later. 22.24 is the grams of a carbohydrate we have, and then we said there's 16 kilojoules per gram, so that's 355.84. This is the least reading time of all time. Okay, so that's kilojoules. We've got fats, which is 8.5 times 37. Sorry. 8.5 times 0.4 times 37, so that's 125.8 kilojoules. And we've got proteins, so proteins are 17. So we're going to do 13.3 times 0.4 times 17. So that's 90.44. So the protein is going to be the lowest out of these. And you could maybe even get a hint of that at the fact that there are two proteins. Don't always use that as a guarantee thing, but normally if there's two that have the same starting thing there and the other's different, it's one of those because they want to give you that basically having to make two choices. One set of 50-50 and then the other 50-50. Protein because it contributes a total of 90.4, so A is the correct answer there. Look, it's the trap answer that I predicted there would be. So that's if you read that as, if you read this value here as one serving, then you'd get B as your answer there. So note that there's typical trends of you can, once you've done enough of these, you can kind of predict what kind of trick answer they're going to come up with. Okay, the equation for the complete combustion of ethane is here. Given the molar mass of carbon dioxide, I said I'm not going to do the quantitative ones. Which is a correct procedure to follow when using a solution calorimeter. After calibration, the heating coil needs to be removed from the calorimeter before use. No, because then it would be a different system than if you didn't remove it. So it would have a different heat capacity. Use the same lid, stirrer, and thermometer throughout the experiment. Sure. Double the calibration factor if the volume of the liquid is doubled. You shouldn't double the calibration factor, as in you shouldn't be doubling the volume of the liquid here. I don't know why you would double the volume of the liquid. Are they saying you're mixing something and trying to find the energy from mixing the two of them together? I don't know. Halve the calibration factor if the volume of the liquid is doubled. Generally, if there's an answer that says do the same thing, it's correct. So I'm just going to go with that one, because why would you use a different thermometer or a different stirrer or a different lid? Okay. I don't know what C and D are really getting at there. This is one of those times where you can see that you've got two of them that are similar, so that might trick you into believing that C or D is the correct answer. So definitely don't jump on, oh, it's definitely the case that it's one of these. But sometimes it can be useful tiebreaker if you've got absolutely no idea or anything else. Alright, let's come back to that later. Oxygen gases bubble through a solution of sulfurous acid. The relevant half equations for the spontaneous reaction are, so it is spontaneous. And we've got two half reactions here. Oxygen gas is a more powerful oxidizing agent than the sulfate ion. Yep. I don't know what said that. That's, oh, okay. It's just saying that this is higher up than this, that this is actually the correct order if you put them in an electrical chemical series. What is the balanced equation for this redox reaction? So obviously the oxygen is going to react with the sulfurous acid. So if sulfate's reacting, then it's not right in the first place. So it's going to be the oxygen and the sulfurous acid. We've got 4 electrons for the oxygen and 2 for the sulfurous acid. So we'd expect A to multiply this by 2. So that's going to be 2 sulfurous acids. And that should, we would make 2 times that, so 8. And we would subtract 4 here, so we would get 4 as a product. And you'd be reacting to water and producing to water, so the water would be cancelled out, which is definitely gives us A there. In the human body, the role of the enzyme in the esterification of fatty acids into triglycerides is best described as a process in which the protein undergoes chemical changes and becomes inactive. That's not an enzyme at that point. Whoops. Provides the necessary chemicals for the reaction to occur. What? Enzymes don't provide the chemicals. Increases the rate of both the forward and backward reaction equally. Yes. Provides an alternative pathway. Yeah, okay. So this one they're saying that the amount that the activation energy is decreased is the same, but exactly what change that would have on the rate would not be equal is what that was going there. So it's almost right in the sense that it increases the rate of both the forward and backward reaction if that wasn't there, but it's not mathematically equal. So D1's better. This is just your definition for a catalyst, so hopefully you go with that one. We've got a reversible reaction. It has an equilibrium constant K of 2 at a given temperature. At that temperature, it contains a mole at a mixture. 1 mole of oxygen is added to this equilibrium mixture and the temperature is kept constant. At the instant the O2 is added, the frequency and success of collisions between, well, you added O, so the only way we would increase this rate is if you increased the sulfur trioxide. Now we did not do that. Now note that you haven't decreased the SO3 either. So nothing is going to change with the SO3. So it's only going to be the O2 and SO2. There's more O2, so there's going to be more things, so it's just going to be C. Alright, which one of the following concentration time graphs best represents the equilibrium system when the system shown below is heated? So it's exothermic. So when it's heated, we expect it to move this way. So we expect A up, B up, C down. So basically we expect 2 things to go up and 1 thing to go down. And we expect one of the things going up to be double the other ones. So here we've got one of the thing going down is double the other one, which doesn't make any sense. On B, we've got, again, thing double going down. That doesn't make any sense. C, we've got 2 going down, so that doesn't even make sense either. And D, we've got 1 going down, 2 going up, and one of the ones going up is double the same amount as the other one because of that 2 here. So there should be, so this one is B if we needed to label it. This one's A, and this one's C. The equation. I don't know why it's skipping between pages. Apologies if it gets cut off the bottom of my recorder as well. That might be some maths, so I'll come back to that later. An alkaline solution is electrolyzed to produce hydrogen and oxygen gas. The half equation for the reaction occurring at the anode in this cell will be alkaline solution is electrolyzed to produce hydrogen and oxygen gas. So remember, the anode is going to be oxidation. Anode is by definition oxidation, so it's not this and it's not this because they're both reduction. So the question is just, are we going to oxidize the water or are we going to oxidize the hydroxide? Now, given that this one produces an acid, I'm going to go with it probably not being that one. Let's have a look at the electrochemical series. So we've got our hydroxide here, and we've got our water. So if there's an option between hydroxide or water being oxidized, it is going to be the hydroxide, and so that is going to be that one there. In a particularly rechargeable battery, the overall equation for the discharge is this below. The polarities of the cathode during the discharge and recharge are, so, that's got nothing to do with the actual battery itself. So cathode during discharge, that's a galvanic cell, so just a cathode, well, its galvanic cell is positive. And a cathode during recharge is the opposite, so that's B. Here we've got a new drug. We don't even get the name of it. I always think it's cool when there's squares in them. Which of the following correctly names the circled functional groups? So X is an amine or an amino group. So that knocks out B and C. Now, the trick here is they're saying that it could be an amide. This is the amide here. The carbon that the nitrogen is attached to does not itself have a double bond O on it. So therefore it's not an amide. So that one I've labeled there is an amide. Y is going to be a ketone. There is no OH over here or here. There's carbons on both sides, so therefore it's going to be a ketone, or you can say that's a carbonyl group there. And then this is a hydroxyl group over here. So this one is going to be D. So I guess I shouldn't say ketone. They do have them in here under the names they would like you to call them. I think there was some debate about exactly what. That's the end of reading time. So you got the class is a ketone and the functional group name is a carbonyl. Yeah. So normally, for the sake of most things, people don't really care. For this one, I guess if you're in a short answer one and they say what's the name of the functional group, use the ones they've got here in the data book here. Alright, so that puts us almost halfway through the multiple choice during reading time, and we definitely could have gone faster if I wasn't trying to explain everything here. Alright, let's start 2.5 hours. I'll see how far I get before I want to go home. In which case I'll come back later. The correct IUPAC name for the compound shown above is, we've got 5 carbons. Well, I shouldn't number them yet. So there's 5 carbons, so it's going to be pent. So if it's not pent, it's out. Okay, they're all pent. Now, we can see that in terms of the answers here, there are 2 that say an aldehyde. Now, there's a carbon on both sides of the carbonyl group here, so therefore it is a ketone. So we're going to chuck these 2 out. Now, the other 2 are basically just, do you number it from the left or do you number it from the right? Basically, any nitrogen or oxygen is always going to be more important than a halogen, so we will number it from the right and go 1, 2, 3, 4, 5, which makes this 4-bromopentan 2-one. Which of the following molecular formulas represents a straight chain fatty acid containing the greatest degree of unsaturation? Okay, so basically we can just look at the ratio of carbons to hydrogens here in a kind of dodgy way of figuring out how many double bonds there are. So in A, the number of hydrogens is 2n minus 4. In B, it's 2n minus 2. C is 2n. D is 2n minus 2. So in the ratio of carbon to hydrogens, A has the lowest because there's a lot less hydrogens. So, for example, B has 2 more carbons but manages to have 6 more hydrogens than A, when we would normally expect it to have 4 more hydrogens. So A must have 1 more double bond than B. And if we compare C to B, it's got 4 more carbons, but it has 10 more hydrogens when we expect it to have 8. So it must also have another double bond less. And then if we compare C to D, it's got 2 more carbons, and it's got 2 more hydrogens. So when we expect it to have 4 more, so it must have 1 more double bond. So A is the answer there. We've got limonene, a compound commonly found in the leaves of some Australian native trees. Okay. What is the most suitable solvent to extract limonene from leaves? Okay, interesting. Obviously, solvent extraction is one of the new topics that's on the study design. This is just a straight up polarity question. If we look at the things on here, you will notice literally everything is a carbon or hydrogen, meaning that this is very non-polar. So this is basically just saying what is the most non-polar solvent? And the answer to that question will never be water, unless the only option is water. Ethanol is very polar. Propanone is a little bit polar. Hexane is very non-polar, so will be the best one there. Enzymes commonly start to denature when temperatures reach 50 degrees or more. Which structural changes are most likely to occur in an enzyme if it is placed in a solution at 50 degrees? So remember, denaturing is to do with the secondary, tertiary, and potentially quaternary, if it has it, structures. So primary is out. Now, covalent bonds in the secondary structure do not exist. They are hydrogen bonds. Intermolecular forces in the tertiary structure will be disrupted. That seems pretty good. Disulfide links present in the structure will be broken. They are part of the tertiary structure, but they'd probably be more stable there. So remember, disulfide links are a covalent bond, so I would expect them to be more stable, especially that it's at 50 degrees. So in terms of things that would start to break, these would be the ones that are first. So they're referring to the disulfide links as kind of intramolecular, even though technically they're all forces that are within the same molecule. Intermolecular we're still using to broadly categorize as dispersion, dipole, and hydrogen bonds. When a single cysteine residue, okay, I wondered why they were leaving amino acids in the data book, is present in the primary structure of a protein. Now, when we see cysteine, you should be able to recognize that and just be like, bang, that is the disulfide bond amino acid. It's present in the primary structure of a protein. Which one of the following shows the strongest type of bond that can form between the R group on this cysteine residue and any other amino acid R group along this chain? Well, it forms disulfide bonds, which are covalent bonds, so the strongest one would be covalent bond, because the only other one they would form is dispersion forces. Sulfur isn't very polar, neither is hydrogen, so you end up with a pretty non-polarish group there. But you can form a covalent bond, which is already stronger than these ones. And would probably be stronger than the ionic one as well, to be honest. There are many chemical pathways in which 2-chlorohexane can be made. Which of the following is the reaction step that could be used to make 2-chlorohexane? Reacting chlorine gas with 1-hexene. Okay, so 3, 4, 5, 6. We've got 1-hexene. We react chlorine gas, so that's Cl2. You get chlorine over both. So that's how you get 1,2-dichlorohexane, which is not what we want. Alright, now we put the double bond on the second one. We break the double bond, add chlorine on both of them. Well, now we've got 2,3-dichlorohexane, which we still don't want. Reacting hydrogen chloride in the presence of UV light with hexane. You would normally do chlorine gas in the presence of UV light with hexane, which might make it. Reacting hydrogen chloride in the presence of a catalyst with 1-hexene. Now that's going to be the best, because we've got a double bond there, and then now the hydrogen's going to go to 1, and the chlorine's the other. Now the chlorine might go on 1, or it might go on 2. So 50% of the time, it'll make this one here. It probably wouldn't be exactly 50 in reality, but for the sake of year 12, we're not talking about why it might prefer one over the other. So It's going to be this one here. Carbon NMR spectrum of a naturally occurring 2-amino acid is shown below. Which of the following could be the 2 amino acids represented in the spectrum? Interesting. So we've got serine, valine, alanine, and glycine. Okay, so I'm looking at this. It's got 3 carbon environments. So what that is telling me actually is that, remember, an amino acid, oops, shouldn't look like that. An amino acid at its core is going to look like this and have an R group. Now we see 3 environments in this R group. So, sorry, we can see 3 environments in this spectrum here. We currently have 2 in this one here. So that means that R must have 1 carbon environment in it. So let's have a look. The other thing I'll note, we've got 2 at 60, so I'm probably not overjoyed to go sifting through which things are at 60, because there's normally, basically, the closer you go to the right-hand side, generally the more things could be that peak. There is a peak around 180. It's probably the carboxylic acid, because it's de-shielded a lot, but we'll double check it. So we should actually, so even before that, actually, we can just have a look at here. Just look at serine, valine, alanine, and glycine, and see which ones of them have 1 carbon environment. So we've got serine. So serine, we can see, has 1 carbon environment, so serine very well could be the answer. Valine has 1, 2 on top of the other 2, because these are the same one. So valine would have 4 peaks. Alanine has 1 as well. So we're actually going to need to compare alanine and valine. Sorry, alanine and serine. And glycine is the last one. And that has 1, 2 environments. So basically the question is, do we have a methyl group or do we have an OH group? A methyl hydroxyl group. So let's have a look at our carbon NMR data. Okay, now we do have one about that 178 there. So let's have a look at what's in there. Okay, our possibilities, we actually have a few, but they're all the carboxylic acid basically, as in that's the only one that would fit there. So this one is the carboxylic acid. So now the question is, out of the methyl group or the CH2OH, which one of them would be at about 60? Now the methyl group one would be at about 8 to 25. Now it's not there. Instead, it's a bit higher. It looks like that one there for serine, and that matches that 50 to 90 range. So one of these is the central carbon here, and one of them is going to be this one here. So serine is the right answer. Okay, we've got a chromatogram. Alright, propan 1-ol, octane, hexane 1-ol, octane 1-ol, and 1-chloropentane. Okay, interesting. They had a non-polar stationary phase, so the basic, and a polar mobile phase. So the more polar it is, the further it'll be to the left here. So we've got 5 peaks and we've got 5 chemicals. That's good. Peak 5 in this chromatogram is likely to be that of, so what's the slowest one, i.e. the least polar? And octane has no polarish groups on it, so that's definitely going to be the least polar. And then you could have a look at the alcohols there. So propanol is probably that one there. Hexane 1-ol is probably that one there. Octane 1-ol is that one there. And 1-chloropentane is probably that one there. These two might be swapped around because the 1-chloropentane is a bit smaller. So that chlorine can have a bit of a bigger impact, but it's not asking that anyway. Okay. In which section of a VCE chemistry poster should a student identify the limitations in their data and method? Alright, so you wouldn't put that in the method because the point of the method is just to be there. The introduction is mostly for theory. not for really talking about your experiment in particular. It definitely goes in the discussion. You could theoretically mention it in the conclusion if it was a critical point, but I think they're definitely going for discussion. Ideally, before a scientist can publish experimental results, the research that has been undertaken should undergo a process in which the experiment is repeated by an independent group of scientists. This process will verify the theoretically it could verify some other ones as well. But they're definitely going to be reproducibility. If you've got the same experiment being repeated by someone else, that's just textbook reproducibility. So it's probably going to be in a different lab and by different people. And if you get the same results, then you would say that is high reproducibility. Yeah, it does say ideally because I'm going to be honest, this doesn't happen. It doesn't usually happen. The following is an extract from a safety data sheet for a chemical that Suresh considered using as an organic reagent. Okay. Okay. According to the information in the safety data sheet above, which of the following statements is the best recommendation for the use of this chemical in a secondary school lab? So what is it? So it's toxic if you eat it. It's toxic if you breathe it. It's toxic if you put it on your skin. It gives you cancer. And it's toxic. Don't put it in the water. And damages the ozone layer. Alright. It should be safe if only small quantities are used. It should be safe if it is only used in a fume cupboard. It is not safe to use it at all due to its long-term risks. It should be safe if the wastes are washed down the sink with a lot of water. So I'm going to say D is out of the question because they say it's a long-term aquatic hazard. Man, this is such a subjective one in terms of what is the threshold for what is safe in a secondary school lab. This is a really bad question. You're supposed to be aware of the statutory limitations that we can have in a thing. Carbon tetrachloride. I can tell you that this one shouldn't be. Legally, I don't think you can use it, given that I don't think you can use chloroform either. That was what I was leaning towards anyway. So it's definitely not A in the sense that it's not safe there. Honestly, this is one of those things where it's like, you're probably fine anyway, but I'm pretty sure from a school perspective, carcinogens, so things that give you cancer, shouldn't be used there. Now, really, are they really assessing that in the exam? I think if this was a question for the actual exam, it would be better written here. Basically, anything that is a carcinogen, I think, is not allowed in school labs or is a significant risk for being a carcinogen. Use these all the time as soon as you start doing stuff at uni. So exactly what's the threshold there? Yeah, again, C. This is kind of a dumb question because the whole point of a safety data sheet is you're not supposed to memorize this stuff. Just look it up. They've literally got a guide somewhere that says, can you use this in a school? Just look it up there. Okay, Ruby investigated how the total surface area of a piece of marble affects its rate of reaction with hydrochloric acid. Okay, here's the equation. Ruby conducted 2 experiments, 1 and 2. In each experiment, she used a different shaped piece of marble, with each having a mass of 0.34 grams. The marble used in experiment 2 had a greater total surface area than the... Okay. Experiment Ruby added 100 mils of 1 molar hydrochloric acid to the marble, collected the gas that evolved in a gas syringe at SLC. She measured the volume of the gas at 20-second intervals. Here's a plot. Okay, that makes sense. It's a bigger surface area, so it goes faster. Whoop. Which of the following is a valid conclusion that Ruby could draw from the graph? Both reactions have reached equilibrium at 160. I guess the question is it an equilibrium reaction? Because this probably isn't an equilibrium reaction and it just all gets used up. In each experiment, both reactants had been totally consumed at T equals 160. Okay, so basically to decide between these, we're going to need point to figure out, let me use my calculator instead. Here. So 0.34 divided by 100.1 will tell us the mass of calcium carbonate. Now, the amount of carbon dioxide is the same as the mass of calcium carbonate. So they're the same mole. I think I said mole. And then, in terms of volume, we can multiply that by 24.8 to get the volume in litres of carbon dioxide that we expect to come out. So then multiply that by 1,000, and we say we would expect 84 mils if it was fully reacted. And that seems to be about what we're getting. I would expect that line to be slightly higher. So 84.2, I'm just going to write that down. And then I'm just going to check the hydrochloric acid to make sure that's in excess. So 1 molar times 0.1 liters is 0.1 mole. I guess that makes sense. And then we would halve that to get the mole of calcium carbonate, and then multiply that by 100.1. So the amount of hydrochloric acid would react with 5 grams of calcium carbonate. So that's definitely not the limitation. You know what would make this a whole lot easier if I read the question. Both reactants. So it's definitely not both the reactants. The hydrochloric acid is in excess, which we just calculated. So that's definitely not right. Now the calcium carbonate had probably been totally reacted, which means it's not at an equilibrium. Just an equilibrium doesn't mean the reaction has stopped. It means that the reaction's going both ways, and there is no more forward reaction. Because if there was still more forward reaction, the carbon dioxide would actually be still increasing more, because the carbon dioxide actually leaves the reaction vessel. So this one actually just cannot reach equilibrium. Okay, the greater the total surface area of the marble, the greater the rate of okay, that was so much reading for the easiest multiple choice one of all time. Alright, the greater the total surface area of the marble, the greater the amount of carbon dioxide gas produced. You could make that argument if it was partway through the experiment, but assuming they're talking at 160 seconds, then D is not right. Alright. The below is an image of the reading on an ammeter used by a student, Leanne, during the electrolysis of a solution. Leanne connected the ammeter so the low scale, the 0 to 5 ampere scale, was used to measure the current. Okay, this one's a really odd one in terms of the fact that I feel like a lot of students won't have used an analog ammeter or voltmeter necessarily. Like, we'll just use a multimeter. Another odd question. Which of the following is correct regarding the resolution value for the data being generated by this instrument and the correct value of the current that Leanne should record? Okay, so we've got 0 to 5 ampere scale. So that's basically, is it the top one or the bottom one? Well, it's 0 to 5, so he's using the bottom one here. Alright, what's the resolution here? So remember, resolution is basically what's the smallest value that you can actually tell the difference between. So there's no way you could tell the difference between 1.001 and 1.002 on this. You couldn't read the difference. We do have tick marks here every 0.1. So our resolution is going to be the 0.1 amps, not the 0.01 amps. So we're going to end up with one of these, and the correct value, interestingly, if the resolution is 0.1, you can't really make a valid claim to 1.05 anyway, I don't think, but anyway. So the correct value is definitely going to be, because we're reading from the bottom, over 1, so the only possibility is B anyway, which is nice. So 0.25 would be if you'd really have to, if you're reading it from the top, this would be 0.25 about here, halfway through it. So, because this is 0.3 here. Yeah, no, you'd have to mess up a lot to get 0.25. Okay, vitamin C can be analyzed using a redox titration, where 2,6-dichloroindophenol solution is used as suitable titrant. A volumetric analysis of a vitamin C drink was performed by a VCE chemistry class, and its titration 20 ml aliquots of the vitamin C drink were titrated against a standard DCP solution. Diego consistently found that he was getting higher results for his titers of DCP compared with all the other students in the class. Aha, the classic rinsing question. Okay, so if Diego is rinsing his pipette with water before each use, that would reduce the concentration of the drink, and that would lead to a lower reading of the drink because there's just less stuff in there. So A would lead to a lower value. Continually rinsing his pipette with DCP solution before each use. That would also react with the drink and get rid of some of the vitamin C. So that would also reduce the concentration of the drink because it's kind of like if you'd already added 0.1 mils of the titrant in before you even started titration. Pipette with vitamin C solution before each use. Is that the drink? Is the drink the vitamin C solution? I assume so. Rinsing his pipette with vitamin C solution. No, that's fine. That's what you're supposed to do. Rinse the conical flask with vitamin C solution before each use. Now this would increase the amount of vitamin C in there. And so if you were pipetting and in the 20 mils there was 1 mole, for example, the droplets that were still in the conical flask might have 0.01 mole in there. So when you aliquot in the 1 mole, you now have 1.01 mole of the vitamin C in there. It's definitely not that much, but you get the point there. So D is going to be the wrong answer there. You can wash the conical flask out with just water, and that's the best. Would be the best thing to do. 4 students recorded data from the experiment. The true value of that. Wow, they're really not making me do calculations. Okay. The true value expected for this titration was a titer of 17.05 mils. Which student was able to obtain the most precise data? That's okay. So this is just a complete red herring. That's for accuracy. You don't need that. Which one is the most precise? So basically, who has the most similar amongst all of their things? So Ben is different by 0.1 each time. Chang. Let's just look at the range for now. So the range on Ben's is 0.3. The range on Chang's is 0.5. The range on Olivia's is what's that? 0.6. Am I reading that right? Yeah. Ravinder is that 1.3? Yeah. So Ben looks to be the most precise. Now, what we could do is we can have a look at them and see if there's one where if you just remove an outlier, whether that fixes the problem. Olivia has 2 pairs that are similar, so that's not great. Ravinder's, I'm probably butchering that name, has 2 that are similar. Oh, sorry, no, they're really, his titration sucks. So they're similar and they're similar, really. Chang, again, you could maybe remove the 15.5 as an outlier and then they're all within 0.25. But overall it seems like they're going with Ben. Normally the answer to these is pretty clear. But yeah, none of these are great titrations. Again, if you wanted concordant ones, you'd go within 0.1 mils of each other. So if I was actually doing this properly, I would throw all of this data out and tell them to do it again. Now, one trick that we could do, I guess, is we could look at the 17.05, and now we know that this is irrelevant and that whoever we know that Vikar's put this here as a red herring, so whichever one is the most accurate, which is Ravender, is not going to be the right answer because it's a trick question. So we know that this one is wrong by virtue of why else would they put that data there if they weren't trying to trick people? So he's definitely wrong. Ravender. Dayu plots data. For some reason, I thought this was some type of graph that we'd never covered. A Dayu plots data generated during an experiment in which she measured the volume of gas being formed over a period of time. Which one of the following plots shows a non-linear relationship? Well, so first up, does it not look like a straight line? That looks like a straight line to me, so I'm just going to chuck that one out. As well as clear evidence of a systematic error being present. So a systematic error, if I was looking at the graph here, I would probably expect a non-zero value at y. That's just a guess of what it's going to be, because you would expect no gas to have been produced at 0. And that's linear, so we don't have that. And lo and behold, we have, I swear I haven't looked at this beforehand. And lo and behold, there's a value that is non-zero at 0. There is no way you have some gas formed before you start the reaction. Well, there is a way there's some gas there. Well, there is a way there's some gas formed, and it's you stuffed it up and you started the reaction, but you didn't start the timer. So C is looking good for that one. All right, let's go back to the top and do those last couple of ones here. Alright, equation for the complete combustion of ethane at SLC is shown below. Given that the molar mass of carbon dioxide is 44 grams per mole, the combustion of 4 moles of ethane under these conditions will produce which of the following? That's very nice that they give you the molar mass of carbon dioxide. Okay, so I keep pulling out my physical calculator. I'm too used to it. 4 moles of ethane, and it's going to make greenhouse gas. Oh, and they've got the trick question. The volume of greenhouse gas is going to include the volume of water because water is a greenhouse gas. So predictable. Okay, so 4 moles of ethane. And we can see here from the ratio, there's going to be twice as much carbon dioxide as there is ethane. So 4 times 2 is going to, so we're going to have 8 moles of the carbon dioxide. The carbon dioxide weighs 44. So we multiply the mole by the molar mass. We get 352. So again, another thing, if you've got time, look at the other answers. If you can figure out why someone might pick the other answer, then that makes you more confident that you got it right. If you didn't multiply the mole by 2, you would get 176. So that's where the 176 came from. And I bet that the 198 is going to be, I'll make a bet that the 198 here is going to be if you just do carbon dioxide, and the 496 is if you include water as well. Let's see how we go. So we said there was 8 moles of carbon dioxide, and there's 24.8 moles liters per mole at SLC, which gives us 198. That's for the carbon dioxide. And at water, we would get 3 times as much as the ethane, so we'd get 12 moles. In fact, we can just multiply these two together, and we can say from the ethane, from 4 moles of ethane, you would have 5 times as much greenhouse gas. So 4 times 5 is 20. I don't know why I need to prove that to you, but there's 20 moles of greenhouse gas multiplied by 24.8 liters per mole is 496, which, there you go, here's D. Okay, Miller performed the following experiment. Add 120 ml of water to a clean, dry calorimeter and monitor the temperature every 10 seconds over 100 seconds. After 100 seconds, apply a current of 1.8 amps with a voltage of 6 volts for 5 minutes and then switch off the power. Stir the solution. Okay, so we're probably going to have to multiply these together, and they've said 5 minutes to make you multiply it by 60 to get the seconds. Using the information from the plot, the temperature change that Mia should use for the calibration is closest to... Wait, you don't even have to use that value. So many red herring data points. The temperature change that Mia should use for the calibration is, it's just going to be, she turned it on at 100 seconds, right? So it's basically just going to be from the starting whatever the lowest value is to whatever the highest value is. So she turned it on, so it got up to there. And it's turned on for 5 minutes, which is 300 seconds. And okay, so the 400 second mark is actually the peak. They're not trying to trick you there. Interesting. So nice. So the difference in the two here is whatever this is, which is like 28.5 or something like that, and 23 at the other end. So the temperature change is going to be 5.5. Now, can I think of... Now, these ones are like... Man, you stuffed up. Where do you get 5.1 from? I think you get 5.1 if you start here. As in, I don't know why the temperature goes down between the fourth and fifth point. That seems odd. Also, why is she stirring the solution afterwards? Monitor the temperature every 10 seconds, over 100 seconds. Anyway, the only place that the heat would have come from is from there, so I don't know why. Where are you getting 5.1 from? Anyway. And we did the rest. Okay. Alright, so that was 45 minutes to... Now, admittedly, some of that was the reading time. So 45 minutes out of the 2 hours 30 minutes for the multiple choice. So that probably took longer than I guess I'd hope, in the sense that each mark you'd probably want to be a minute and a bit. So probably want that to be maybe 40 minutes or so. So that was okay. Alright. In a school lab, let me just read the instructions. Anything different there? Simplified answers to all numerical questions with an appropriate number of sig figs. Unsimplified answers will not be given full marks. Okay. So I think that just means that if you leave like a really unrounded one, then you won't be given a full mark. Sure working your answers. No marks will be given for an incorrect answer unless it is accompanied by details of the working. So at the end of the day, if you've got the right answer for a 3-mark question, then I think they still give you the 3 marks. It's just that showing the working out protects you against losing all of the marks if that value is wrong. Ensure chemical equations are balanced and the formulas for individual substances include an indication of state. Okay, that's always been the case. In a school lab, Amelia and Dylan fermented plant biomass and then distilled it to produce bioethanol. State which one of the 7 principles of green chemistry is the most relevant to the production of bioethanol from fermentation. Use item 26.2 of the DUDOC. That is... Wow, that's generous. They even tell you the page number. Alright. Alright, which one is this? It's use of renewable. Okay. I don't think there's any argument for literally anything other than use of renewable feedstocks. They give you the definition there. Okay. Here's an equation. Calculate the percent atom economy for the production of bioethanol from glucose. Man, they're so nice giving you all these molar masses. Wow. I guess that's nice in the sense that it just reduces the time. So remember, atom economy is going to be the molar mass of the product you want divided by the molar mass of all of the reactants. So in this case here, we're going to have 2 times the ethanol molar mass over the glucose one. So that's going to be 2 times 46, and then divide that by 180, which gives us 0.5 times 100. So I'll multiply that by 100. I miss my usual PowerPoint thing where it just drops out the whole letter in one hit. I'll just multiply it by 100. Obviously I could have done that on here. 51.1%. We've got 4 sig figs here, 3 here, 3 here, so I'll give this to 3 at the bottom. Calculate the percentage yield of ethanol if 100 grams of glucose reacts to form 7.15 grams of ethanol. Okay, so this is going to be our experimental yield. So just a reminder that the formulas are up here, actual yield over theoretical yield. Okay, so, sorry. Experimental is what we always refer to as uni. You could call it the actual yield as well if you want to. Alright, so really, the only other thing we need is the theoretical yield, and then we can just jam it into our equation here. So 100 grams forms 7.15. So basically, what mass would we expect of ethanol? And here's our equation here. So we've got... So I'll do my work in here. So we want to figure out the amount of ethanol that we would expect. To do that, we're going to know the amount of glucose that we're reacting, which is going to equal mass of glucose. I'm going to write this out here. You could probably get away with not doing it. So we've got 100 divided by the molar mass, which is 180. There you go. So 0.555. I'm going to leave that in the calculator. Now the amount of ethanol, again, if you want to put like theoretical down there or something like that, you can, equals the amount of glucose times 2, which is going to equal 0.555 times 2, which is going to equal 1.111. And then the mass of ethanol, again, theoretical, equals the amount of ethanol, theoretical, times the molar mass of ethanol, which is going to equal 1.111 times 46, times 46 is going to be 51.1 grams. Again, probably don't need to use that much space. Okay, so basically we expected 51.11 grams. We got 7.15. So the percent yield is going to be, I'll write actual just to fit with their equation. Do they say theoretical? Yes. 100 over 1. That's unnecessary. Anyway, is going to equal 51.11 over, sorry, it's going to be 7.15 over 51.11 times 100. Again, use your answer there. It's just harder to do in this one. So is going to equal 13.99. So round that up, and it'll be, I'll put 3 sig figs, 4 sig figs, so I will do 14.0% there. It's not an amazing. Explain why fermented biomass required distillation by Amelia and Dillon to produce usable bioethanol. So basically, the reason is just that there's a bunch of other stuff in there, and when you combust it, you want to be combusting pure bioethanol. So what would I expect the 2 marks to be? I'd expect there to be a mark about separation. What's the other mark there? So my thought process will be something like the biomass has a bunch of stuff in it. Um, Needs to be pure to burn efficiently. Honestly, you could probably not say this. It'd probably be fine. And distillation is used to separate the bioethanol from the other components. That's what I'm thinking there. Okay, if you've got another answer you want to give, I guess leave a comment or something. The following thermochemical equation shows the complete combustion of methane. Yeah. Activation energy for this reaction is 230. Draw an energy profile diagram for the complete combustion of methane gas. Indicate on the diagram the delta H in the activation energy. Okay, so we're going to need to go down 890 from our original point, and we're going to need to go up 230. So let me just count what we've got. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so negative 900 or negative 890 is going to be about here. Again, bring a ruler. Going up 1, 2, 230 is going to be our peak. So if I pick somewhere roughly in the middle, so and go about 230, that's probably fine. And then I go up and I come back down, and you have the most beautiful energy diagram of all time. Look at that, we've even got like a transition state here or something like that. Okay, interesting. Hopefully you can draw a better picture on your thing. Anyway, yes, it's exothermic, so we've gone down 890. Assuming I counted that correctly, I'm not going to bother double checking it, and it goes up 230. You should double check it. I'm not going to. So there'd 100% be a mark for being at 230 at here, and there'd be a mark for being at 890 at the other end. And I assume if you just didn't draw the curve, they'd take off a mark or something like that, or take off both marks. Okay, a two-step reaction mechanism takes place where the tertiary haloalkane 2-methyl propane reacts with sodium hydroxide in a substitution reaction to form an alcohol. There are two reactions. Oh, it's a reaction mechanism. I love it. Not quite. The bond between the carbon and the chlorine is broken, and a new bond between the C and the OH is formed. Interesting. So they're referring to this in terms of an SN1 mechanism, which is accurate for a tertiary haloalkane. Alright, write the balanced overall equation using semi-structural formulas. States are not required. Oh, they're using the bond enthalpies. Okay. Cool. I wondered what that part of the data book was for, and okay, it was a logical thing. They weren't going to try and trick you with it. I like this telling you what part of the data book to go to. Balanced overall equation. Anyway. Okay, so really, if I want to do a semi-structural, I am looking at the largest chain and just seeing what comes off it. So it looks, even though there's 3 coming from the same thing, effectively it's just one, just propane, and then an extra one coming off the side. So if I'm doing a semi-structural, and I want overall, so I can actually just completely ignore this, it's called a carbocation in the middle, and I can just do this. So we've got CH3, and then we've got C, and then our stuff. We've got a methyl group and a chlorine attached there, and then we've got a methyl group. And they react with sodium hydroxide. States are not required. They're not normally required for the organic ones. So write them in like that, and then we get sodium chloride out here. I'd imagine forgetting the sodium hydroxide, the sodium chloride would be a common mistake. Alright, here we go. Item 10. Oh yeah. I was hoping they'd show where they might use one of this. Okay. Identify whether this process is going to be exothermic. I actually thought this might be how they used it. I did look up these values and they didn't actually match the. If you do it for the combustion ones, they don't quite match. So I think that, but maybe if you assume the solvation is the same, like the solvent around them has the same interactions. So we're just assuming this molecule doesn't exist in anything else. It's just a molecule floating around in space. Okay. So basically, the delta H is going to equal the bond we formed, the strength of the. I shouldn't do that at all. Of this one minus this one here, because we're breaking that one. Gee, I don't love this question because I guess we're assuming that the sodium hydroxide is dissolved and that we're assuming the sodium chloride is dissolved. I guess, and that and that we're ignoring the water interactions. Okay, so what's the strength of the carbon-oxygen bond? Let's go carbon-oxygen, 358 kilojoules per mole. And what's the energy of the carbon-chlorine bond? Carbon-chlorine is going to be 324. So therefore, the difference is 34 kilojoules per mole. You know what, I should have done those the other way around. So the delta H will be the negative of that, because if the one being formed is stronger than the one being broken, we should end up with a negative result. And that makes sense there. It especially makes sense because we know that this is a reaction where you can chuck the sodium hydroxide in and it will react spontaneously to do this quite favorably. So negative 34 kilojoules per mole, so therefore exothermic. Identify usually just is basically state that, so I can just say exothermic. The rate of this reaction is controlled by the first step in the mechanism. Oh man, this is cool. I like this. The rate of this reaction is controlled by the first step in the mechanism, the breaking of the carbon-halogen bond. That makes sense. Explain whether the reaction between 2-iodo-2-methylpropane with sodium hydroxide would be predicted to react at a faster or slower rate than 2-chloro-2-methylpropane under the exact same reaction conditions. So you might say, well, what am I supposed to do there? So the difference is just, this is actually linking back to 2. They're trying to scaffold the answer for you. So instead of the carbon to chlorine bond, we want to look at the carbon to iodine bond. So the carbon to iodine bond is 228. So is 228 kilojoules per mole. Carbon chlorine is 324 kilojoules per mole. So Ci bond breakage has a lower activation energy, so likely faster rate, therefore 2-iodo-2-methylpropane reacts faster. Wow, if only I could stay on the line. I'm not sure if I think that's a 3-mark question. There's 2 marks there, because I've definitely explained it there. As in, there 1 mark for saying faster, 1 mark for saying lower activation energy. I guess that's kind of 3. Hydrogen chlorine fuel cells are being investigated for potential use for grid-scale energy production. Aqueous acidic system They've given us a nice H plus in there. A diagram of the fuel cell is shown below. Identify the energy transformation that takes place in this fuel cell. It's the same one that it always is. It's chemical to electrical. Write the balanced half equation for the reaction occurring at the cathode. So, okay, let's have a think about the two things. Let's look up chlorine. Okay, so we can just think about what is chlorine going to be. Well, the only place chlorine is on the whole series is here, and that makes sense. So in the sense that we would want it to be at the top left or bottom right, otherwise it's not going to make much electricity. So, and it's the thing that's going to be reduced. And we know reduction is at the cathode, so therefore this is the cathode, and therefore this is the anode, which also makes sense because we know that the hydrogen is becoming H+, and if H+, we could also say we know the chlorine is becoming Cl negative, so it must be getting electrons, and this one must be losing electrons. Okay. Now, write the balanced half equation for the reaction occurring at the cathode. Okay, I just did it. So we can just literally tear this straight off this. Remember to put your states in. Don't put a reversible arrow here because that's not the one that we're intending. That's not the reaction that we're caring about here. It is technically reversible, but you wouldn't really get the reverse reaction happening much, especially because the potential is so high for this reaction. An arrow in the box shown on the diagram above to indicate the direction of flow of electrons in the wire. It's always going to go from anode to cathode, so it's going to go up. So it's always, when I've got a box like this, it's next to the wire there. Honestly, this box should be a bit smaller to try and emphasize that it's talking about this wire here and not the one on the top. But what can you do? Write a better exam is what you can do, but sure. Calculate the voltage that this cell would be expected to produce when operating under standard conditions. So let's just have a look at what we've got. So the chlorine is 1.36, and we want to subtract oxidation reaction, and you might remember that hydrogen is just the comparison point anyway, so hydrogen is just always going to be 0 for the direct oxidation or reduction of it, not just when it's involved in other things. So it would be expecting to produce 1.36 volts. Don't put the greater than, that's for if it's electrolysis. State one design feature of the electrodes used within a fuel cell that would increase the efficiency of the cell. So I would say either electrodes made of catalysts, or you could say refer to porous electrodes. Now it's state, so I'm not explaining why that increases it. Both of them would increase the reaction rate. A similar fuel cell is used in a school lab, operates for 3 hours at a constant current. The equation for the overall reaction in this fuel cell is this. Under SLC, a total of 350 mils of oxygen and 450 mils of hydrogen was pumped through the fuel cell. Determine which chemical is the limiting reagent. Okay. So, remember that both of these are the same. So you might be tempted to think, well, the oxygen's a lot heavier, but that's not actually going to come into play here. So we've got 350 mils of oxygen. Yeah, you don't even need to do the calculator. I'll show you here. But 350 mils of oxygen, we divide by 24.8, so that there's 14.11 moles of oxygen coming in. Okay, and 450 divided by 24.8 gives us 18.14 moles of hydrogen. Now, the thing is that you would expect that this much oxygen, 14.11 mole of O2, reacts with twice that. So it's actually going to react with 28.22 mole of H2. 18.14 is less than 28.22, therefore hydrogen is limiting. So even though there's more hydrogen, it's still limiting because you need twice as much of it, and there's not twice as much hydrogen as there is oxygen. Now remember, we're looking at gases here, and there is no mass involved if we're just going between a volume and an amount. So you don't need to even use the molar mass here. Calculate the volume in liters of the unreacted gas. Okay, so basically, the amount of hydrogen reacted. So amount of hydrogen equals 18.14 mole. The amount of oxygen that reacted, I cannot spell on this thing, is going to equal 18.14 divided by 2, which is going to be equal to 9.07. Just check it so I don't make a silly mistake. So 9.07 mole of the oxygen will react. So amount of oxygen unreacted is going to equal to how much we had at the start. So I'll say the initial minus the amount that reacted. Again, I'm showing more working out than you probably need to here, just so you can get what I'm doing. 14.11 minus 9.07. I could probably do a lot of these in my head, but don't leave it to chance. Doing it in your head and then doing it on the calculator is probably the best thing as well. Alright, 5.04 moles, and we want the volume in liters. So the volume of oxygen is going to be 5.04 times 24.8. So you know what I did? These are mils, and I've been treating them as liters the whole time. Anyway, so basically all of my values are off by a thousandfold, but that's fine. So when I multiply it back to the end, it will actually give me the value in mils. So that's how many liters there are, and then we multiply it by the 10 to the negative 3, which is the same as dividing by 1,000. So we get down to 0.125. Is that how many sig figs we had? This counts as 3 in VCAA's reckoning, and so does that. So yep, 0.125 liters at the end there. So if you're off by an order of magnitude, you can actually fix it. You've just got to realize it. Okay. A biodiesel consists as a pure sample of a fatty acid methyl ester. The molecular formula of this compound is C19H36O2, and its molar mass is 296 mole. Calculate the mass in grams of iodine that would react with 100 grams of this biodiesel. So this is the thing that they were saying in terms of using iodine to determine the level of unsaturation. As a pure sample of a fatty acid methyl ester. So if we think about it, I should probably know this formula off by heart in general anyway. It's going to be CH3 there, and then it's going to be basically a bunch over here. So if I subtract the methyl ester bit off, I subtract 2 carbons, and I subtract 3 hydrogens, and I subtract the 2 oxygens. So this is the formula of the chain bit that I have here. Now, I expect 2 hydrogens per carbon, except the N, which there should be 1 more. So I would expect C17H35. Now I'm missing 2 hydrogens, so that tells me there is 1 double bond there. So we would expect that the amount of, I'll call it the fame reacted equals the amount of iodine reacted there. That makes sense, doesn't it? Yeah. Okay, so we've got 100 grams of it. So basically we want the mole of the fame is going to equal the mass, which is 100 grams, over its molar mass, which is 296, which is going to be equal to 0.334, what? 0.338. The amount of iodine is going to equal the amount there, which is going to equal 0.338. There's no trick here, right? And then the mass of iodine is going to equal the amount of iodine times the molar mass of iodine, which let's go have a look up. Iodine is 126.9. So 85. Oops, I forgot to actually write down what I think was. That's 127, 254. 85.74. So 85.7 to 3 sig figs. Okay. Using molecular formulas, write the chemical equation for the reversible transesterification reaction that produces this biodiesel. Assume that 3 identical fatty acids form this triglyceride. So we've got to use the molecular formulas. So it's going to produce the biodiesel. So we're going to have C19H36O2 is going to be a product, and we're going to have the basically it's going to react with methanol, 3 methanols, and it's going to produce glycerol at the end, which is going to be C3 is H8, right? O3. If you're not sure, there's a nice glycerol there for you. That's 8 H's. That looks good. Okay, write the chemical equation. I'd probably maybe something like this. I assume they're not going to use the states for this one. So if we basically if we look at this here and we want a molecular formula, that's cool. We're going to make 3 fatty acids. So all right, what have we got? We've got 3 lots of 19, so 57 plus 3 is 60. Okay, that's nice. We've got 36 times 3 plus 8 is going to be, oops, that's my mistake there. So, sorry. So if we look at the carbons, there's 60 on the right, and there's 3 in the methanols on the left, so this should actually be 57. And then if we look at the hydrogens on the right, it's 36 times 3 plus 8 from the glycerol. And then we've got 3 lots of 4 from the methanol, so that's 12. So we subtract 12 and we'll get 104. You could draw out the whole molecule as well if you wanted to. And on the right we have 6 oxygens from the fatty acids, or the methyl esters I should say, and 3 from the glycerol, so that's 9. There are 3 in the methanols, so there should be 6 in the original one, which makes sense because it's triglyceride. They should always have 6. I would make that as a liquid if it's in an alcohol. I don't think they're going to look at the states for that one, to be honest. Explain one way that the yield of biodiesel could be maximized. 2 marks. So a bunch of different ways you could do this. Add excess methanol might be one. This will increase the rate of the forward reaction. More than the reverse, increasing the amount of products and thus amount of the fatty acid methyl ester. I would establish what that acronym meant if I was actually writing for an examiner. You could remove the glycerol. You could also remove the fatty acid as the methyl ester as it's being produced. They don't give you any. If they gave you the energy information, you could say something about heating it up or something like that as well. Would all be things here. I don't know why they've told you it's reversible here and then they told you it's reversible again. I guess they were just drawing your attention to it. The energy content of biodiesel was investigated by 2 students, Barani and Jack, using the equipment shown below. They ignited the biodiesel under a beaker containing 200 grams of water, which is set on a tripod. Okay, 0.51 grams of biodiesel was burned. Barani recorded that the initial temperature of the water was 22.2 degrees Celsius and the final temperature was 35.7 degrees Celsius. Assumed that the biodiesel is fully combusted and the system was known to operate with a 55% energy transfer efficiency. Calculate the energy released by the biodiesel in kilojoules per gram based on the experimental results. Do we have to do anything more? Viscosity after this. Okay. Ooh, ibuprofen. I don't want to get a hold of myself. Ahead of myself, even. Probably want to get a hold of myself. Okay, so we're not using a calibration factor here, so we are looking at our equation that's up here, Q equals mc delta T. So we need m and c and delta T. We start with C, so the first thing I probably look for is delta T. It is just what's the difference between the 2 temperatures. Is going to be this, so 13.5. Again, double check myself, 13.5. If they line up, then I can be pretty confident that at least my basic calculations were correct, because that's probably that is a very good way for people who are otherwise quite good at chemistry to lose some random marks. Our mass is 0.51 grams. Remember, I almost made the same mistake I was just about to say. That's the mass of the biodiesel. What's the mass of the water? Oops. Okay, there's 200 grams of water. Don't make that mistake. Q equals 200 grams of water. And our C is 4.18. Let me flag it on here. Here we go. 4.18 joules per gram. And we multiply by the change of temperature, so 13.5. So our Q value overall is going to be 200 times 4.18 times 13.5, which is that in joules. I'm going to divide it by 1,000 to get kilojoules, so 11.286 kilojoules. So energy content, so I'll say my delta H is equal to Q over M, where M is the mass. So Q is going to be 11.286 kilojoules. The mass is 0.51. So we take that, divided by 0.51. We get 22.13 kilojoules per gram there. And the one thing that I haven't done, which is that third mark, is factor in the 55% energy transfer efficiency. So you could have done this. I could have done this before, and basically divided by the 55%. I can just do it now as well. So that's like the effective one, in the sense that that's what the actual energy you get out of it is. So if I say that's the true one, or I should say, I'll just do it over here. The effective delta H is going to be equal to the true delta H times 0.55. So therefore the true delta H is equal to, again, you wouldn't need to actually show this, I'm just writing this out to prove it to you guys. And you can see, even if you realize you've made like that's not really a mistake here in the sense that I knew I had to come back to it anyway. But if you do something where it probably would have been more efficient to do it another way, you can normally still salvage it at the end. Maybe there's an argument to do some calculation on the side first or something like that, but we are racing against the clock as well. 40.23 or 40.24 kilojoules per gram, and we've got 3 sig figs, 40.2 kilojoules per gram. I guess the argument is, do we include the 55% energy transfer efficiency? And I'm going to say no. The following 3 molecular formulas represent members of the same homologous series of a fatty acid methyl ester. Explain how the viscosity of these compounds will vary. So as the size of molecules increase from this one to this one to this one, the strength of dispersion forces will increase. The stronger the dispersion forces, the slower, or you could say more friction, the slower molecules will move past each other, leading to higher viscosity. And just to make it painfully obvious, there we go. So basically just bigger things have more electrons, so therefore there's more strength between them, so they're basically not going to move as fast when they're around. So I'd say there's probably one mark for talking about stronger dispersion forces, and then another mark for basically saying, you could probably just say that and you'll get a mark, and then relating that to dispersion forces and size somehow. Okay, inflammation is a physiological response that causes swelling to occur around an injury. Also, can I just comment on the length of that question? 13 marks. I am sick of biodiesel now. Alright. Anyway, so the swelling, ibuprofen is a common anti-inflammatory drug. It can exist in 2 slightly forms. Only the S-ibuprofen form is biologically active. When your body feels pain, it responds by producing prostaglandins that then cause inflammation around a pain center. Okay. S-ibuprofen is a weak competitive enzyme inhibitor. It inhibits the enzymes that form prostaglandins, which in turn limits inflammation. R-ibuprofen has little impact on the body. So the melting points will be the same, is a mark there. uh, they I'll start with they are optical isomers, so have the same size, bonds, and polarity. If I want to be really clear, shape, size, bonds, and polarity. So same intermolecular forces. Requiring the same energy to break them and cause the substance to melt. Explain by referring to substrate-enzyme interactions what is meant by the description of S-ibuprofen as a competitive inhibitor of an enzyme. You may use diagrams in your answer. Substrate-enzyme interactions. So I mean, if I'm going to draw a diagram, that's this is not the best platform to draw something on. So an enzyme will only catalyze the reaction of a substrate that is complementary to its active site and can bind to it. I draw a nicer picture of, I draw something like the ibuprofen in there, and then the substrate bouncing off it or something like that. Except this is too small. Complementary to its active site and can bind to it. S-ibuprofen can also bind it doesn't tell you what the substrate is, right? Bind the active site. You know what, I could probably just write in this, couldn't I? That would probably make a whole lot more sense. S-ibuprofen can also bind to the active site while it is bound. The substrate cannot bind, so cannot be catalyzed. I probably should have figured this out beforehand. Oh, I can write in that bit, but not in this bit. Yeah, no, okay. State one reason why R-ibuprofen is not effective as an anti-inflammatory. So, R-ibuprofen is not the right shape to bind to the active site. Not complementary. Structures of naproxen and morphine are shown below. Like ibuprofen, these drugs can be used for pain relief. State which molecule would be most likely to work via a very similar pathway to S-ibuprofen. Give a reason for your choice. So looking at these guys, and then looking at these guys, the naproxen just looks like the other ones, right? As in, it's kind of, if you rotate it 180 degrees around that way, like if you've got a carboxylic acid with a methyl group hanging off it. So this bit here actually looks very similar to the S-ibuprofen. It's got an extra ring, and it's got an ether over here. So this bit's a bit different, but this bit is actually basically the same. So naproxen is a similar shape to S-ibuprofen, so would be the most likely to bind to the same or similar active sites. Alright, what do we got left? 6 marks there. Oh, 14 marks there. Oof. 12 marks there. And 9 marks there. Okay. Kelly connected two electrolytic cells in series to the same power supply as shown in the diagram below. The electrolytes are respectively 0.1 molar solutions. Both cells use inert electrodes. Okay. The gas produced down as it's collected and stored at 25 degrees. Wow. Okay. Okay, I guess this is one thing I haven't stressed enough because I didn't think it would come up in the chemistry on, but I guess they want you to be able to recognize that bit of the circuit diagram, which I always mess up because because in terms of current flow we think about it oppositely for chemistry and physics. I'm pretty sure physics goes that way, so therefore chemistry would go that way in terms of the actual electron flow. I'm going to cheat and pause for a second. Actually, not. I'm just going to look it up here because I don't want to answer the whole question and get it the wrong way around. I should say that I think the long one is the positive one. Yeah, and I'm right. Okay. Just didn't want to spend the next 5 minutes doing this question and have it be completely wrong. Okay, so the long one is always the positive one, and the short one's the negative one. So if this is positive, that means that's positive, and that's negative, then this means that's negative, and then we can do the opposite ones around there. And it's electrolytic, so we know that the negative of an electrolytic is the cathode. So therefore this is the anode, and this is the anode, so that's the cathode there, or a cathode. Kelly set up the cell so that all the gas collected produced at the anodes is collected and stored at 25 degrees in a single gas container. Kelly passed the current of 10 amps through the circuit for exactly 5 minutes. Calculate the amount in moles of electrons passing through the circuit. So we can remember that charge is going to be equal to current times time. So that's 10 amps times 5 minutes times 60 seconds. So that's going to be 50 times 60, so 3,000 times 5 times 60. So that's going to be 3,000 coulombs. The amount of electrons equals Q over F, which is equal to 3,000 over 96,500, which is going to be 0.031. And it's 3 sig figs here, so it's 311. Determine the mass of aluminium produced. So aluminium would have a half equation that looks like this because aluminium is 3 plus. So the amount of aluminium is going to equal the amount of electrons divided by 3, which is going to equal 0.0311 divided by 3, which is going to equal 0.01. I guess if I want to keep the 0.01 04. If I want to keep the 3 sig figs running. Identify the gas being produced at both anodes. So what do you got? Copper and nitrate. So both of them are going to be oxidations. Now the only other thing that's in there that could be oxidized, because you can't oxidize nitrate, it's already fully oxidized, and also it's not on the half equation, so you wouldn't expect it to be. The only other thing in there is water, which, I mean, it's aqueous, so it's obviously going to have water in it. So let's have a look at our data book again. We've got water being oxidized is going to be right up the top, and it's going to make oxygen gas. Probably didn't need to say gas there. Determine whether the same quantity of gas will be produced at each of the anodes. Justify your answer. I don't know how you determine that. As in, the answer is yes. So this is just how circuits work. So the current is the same at all points of the circuit. If current and time are the same, that looks like it's saying insane, and amount of electrons be the same, and thus amount of oxygen gas. I'm not quite sure what they're looking for that one, in the sense that that's just how a circuit works. So there's the same amount of electrons are going around everywhere. Like, it wouldn't make sense if you couldn't have 5 moles of electrons go around this way, but not around here. Sorry, it's the anode, so it's coming out of it. But you couldn't have 5 moles of electrons come out here, but then 2.5 moles here, because where have the other ones gone? And same with the power source. You can't have 5 moles come out here and 2.5 moles come in here, because where'd the rest of the electrons go? As in, like, you'll have a massive buildup of negative charge over here. So they're going to be the same. Alright, here we go. Question 7. Compound P is a linear unbranched hydrocarbon containing only 4 carbons and a single functional group. Okay, that is a lot of letters. Maybe this is their new organic pathway diagram. 4 carbons and a single functional group. Okay. It was reacted. Okay, it had water and phosphoric acid. So basically, from that already, I know that it is going to be an alkene. Now, now it's unbranched, so I know it's going to be butene. If it was butene, this would always make a secondary alcohol, because you could add it here or add it here and it'd be the same thing. Because we've got 2 separate products coming out here, I can tell that it must be but-1-ene, because one of these is going to be a primary and one of them is going to be a secondary, and then this is probably going to be the aldehyde and this is the carboxylic acid. Let's see if I'm right. Okay, same oxidizing agents was reused for reactions indicated by 1, 2, and 3. That's what I was talking about. A separate test when compound P was reacted with bromine, a colorless solution was produced. Okay, that was already predictable. State the homologous series to which compound P belongs. It is an alkene. Probably should do that one given it's the most important letter there. After compound P was reacted with steam, two different organic products Q and S were obtained. Compounds Q and S both contain a hydroxyl group and are structural isomers of each other. I mean, that's what we said. It's butan-1-ol and butan-2-ol. Identify a chemical test that can be used to confirm the presence of the hydroxyl functional group through an observable color change. Describe the expected color changes that would be observed. React the product. I'm not very good at remembering these ones because I've just never used them. I've just always used spectroscopy. Let's have a look at some colors. So the one I'm thinking of is if you have dichromate and you react it, it should go from orange to blue. So it should go from the dichromate to... They're saying green. Alright, let's just say green. It was blue when I did it. We could also say permanganate from intense purple to a very pale pink. Wait, why is manganese 2 in here twice? What? Am I missing something? Yeah, okay. I think the green's probably a bit easier to see in the dichromate. Oh yeah, it's just confirming the presence of the hydroxyl functional group, so we don't need to say secondary versus primary. So react the product with acidified I'll give them a salt just in case they're in a bad mood that day. With acidified dichromate, if an OH, I should say hydroxyl. To point out that it's not a carboxyl OH, is present, the orange will be reduced to green chromium 3+. Hopefully me saying this out loud is more legible than my handwriting. Based on the information provided, explain why both Q and S cannot be classified as tertiary alcohols. Tertiary alcohols cannot be both Q and so tertiary alcohols, you can't oxidize them, and both Q and S are further oxidized, so it cannot be tertiary. I don't know why that's 2 marks. That's what I'd be thinking. Compound Q was isolated. Do we not get a full question of spectroscopy? Oh. Compound Q was isolated, and so which one was Q? Q is the ketone. Sorry, no, not the ketone. The Q is going to be the secondary one. So Q is going to be that one. It feels really weird answering a whole question when I already know what the answer is. And hydrogen NMR was conducted to determine the structure of the alcohol produced. The table below provides the details of the peaks produced. use the integration curves, show directly above each set of peaks in the hydrogen NMR spectrum to verify that the peak present at 1.46 ppm results from the presence of two equivalent hydrogens. So this would basically be measure the height. So I'd basically just I don't have a ruler, I can't use a ruler on the screen, but I would measure the heights of all of these, divide them by the smaller one, and you should end up with this basically being 1 to 1 to 2 to 3 to 3. Technically, it doesn't verify that it's 2, it just verifies that it's got a ratio of 2 to the other ones, but given that we know that it's got 4 carbons in the thing, that's pretty fine evidence there. And we expect this to be 1, 2, 3, have 2 3s, a 2, a 1, and a 1, which is what we get in our ratio here. So that is a new one. They've never asked you to use the integration curves in that sense before. And I'm going to be honest, I've never done that either, because when the machine does this for you, it also just calculates the integration curve for you. So a bit of an odd thing they've added to the curriculum there, but it is there. Draw a skeletal compound for compound Q. Okay. Draw a structural diagram for compound S, an isomer of compound Q. Is this the other one? Yep. An IR spectrophotometer was used to analyze product U. Which one's that? Is the carboxylic acid. Name the functional group present in product U. So now this is one of those ones where they require you to use the language of the functional group name. They're saying it's a carboxyl group as the functional group. So carboxyl group. To identify on the spectrum the two absorption regions associated with this functional group. So it's 100% just the OH here and the C double bond O. So basically, just to be super clear, I'll just copy it out from here. So the acids is 1680 to 1740. Oh, identifying the spectrum, the two absorption regions. Do they say acid in here now? Oh, they do. Yeah. And there we go. That's a very generous 3 marks. You had to like full on explain IR for the 3 marks for this bit last year. Not that this is the actual exam anyway. The mass spectrum of molecule T is shown below. That's the aldehyde. Identify a possible fragment that has produced the peak at 57. Okay. So molecular ion peak is 62, 64, 66, 68, 70. So this is 72, which I think makes sense for our molecule. So what do we need to get to 57? We need to lose a methyl group. Okay. So basically we should end, if we subtract the methyl group from there, we'll end up with 3 carbons, 5 hydrogens, and an oxygen. That makes 36, 41, 57. So that one makes sense there. It's also not quite as common as like the 43, which also makes sense. Given that chopping this off, I would predict to be make the most stable fragments, because this can support a positive really well. State what the M over Z symbol means on this mass spectrum. Mass to charge ratio. I.e. it's the mass for singly charged ions. Okay, cool. Man, we didn't even have to figure anything out there. I already knew what all the structures were at the start. The following equation shows the reaction between oxalic acid and potassium permanganate, KMnO4. Direct titration between potassium permanganate and oxalic acid is not an effective method of analysis because this reaction is quite slow. Sam developed an alternative method for the analysis of oxalic acid. Here's his hypothesis. Potassium permanganate is purple using a colorimeter. Okay, therefore the new method is valid. A plot of rate of reaction versus oxalic acid should show a positive relationship. Okay. Explain whether Sam's hypothesis provides a clear focus for this. What does that even mean? Oh, I guess it's just saying that the hypothesis is not clear. Okay. Um, it's a reasonable kind of intro statement. I guess the last bit of the thing is clear. Like, I don't know whether they're saying, oh, you can write this in a hypothesis. Like, I wouldn't. I'd be like, the last part is clear. A statement that can be directly compared to the evidence. Because basically you want to be able to say, does our data match our hypothesis? Yes, no. To determine whether it is supported. He sets up a series of experiments. Now, I don't know why there's all this here. It makes sense, but I wouldn't write that as a hypothesis. In each experiment, the potassium permanganate and sulfuric acid concentrations were set at a fixed value, and Sam only altered the concentration of oxalic acid. Whenever Sam changed the concentration of oxalic acid, the experiment was repeated 3 times. Sam made a total of 5 changes to the concentration of oxalic acid. In every experiment, the volume of all solutions used was kept constant. Okay. Identify a variable that has the greatest potential to affect the rate of any reaction, but which has not been controlled or referred to in his experimental design. I don't think he reversed the temperature. That's just first thing that comes to mind when you're looking at rates is temperature. Explain in terms of reactant particle collisions why the variable. Okay, that's even nicer. Okay. Temperature. It's 2 marks. Will affect how much kinetic energy particles have. Thus, it will affect both the number of collisions. I keep saying number of collisions when I say this. I should say frequency of collisions and the success rate of collisions. Thus, will affect the frequency of successful collisions and thus rate. Here's dependent variable. Sam collated all the data generated, processed the raw data, and plotted the resultant values as shown below. Sam made the following claim about the plot. The plot rate of reaction shows clear evidence of a good experimental design through the production of a very consistent trend in data, little variation of data within each trial. Comment. Man, I really hate questions that just say comment on it. Clear evidence of a good experimental design. I'd say that the low variation indicates high precision. I should say and consistent trend. I don't know. Seems okay. I normally say something like it doesn't provide information about the accuracy. Now that might be enough to get a mark. Honestly, I don't think that's really the point of the experiment, in the sense that the true value doesn't really matter here. The point just matters what the trend is in terms of his actual research. Now I'm trying to figure out whether there's 2 marks because there's 2 dot points there. The production, that's a spelling error. The production of a very, I guess I can just say Sam made a spelling error. The production of a very consistent trend in data. Clear evidence of a good experimental design. I guess it doesn't provide information about accuracy or validity, really. Or reproducibility. They'd be the things that I'd be thinking about, in the sense that it shows that he can have high precision, but it's not really indicative of the other ones. The data looks pretty good for now, though. Justify whether the data shown in the plot supports Sam's hypothesis. The data shows a positive trend. As higher oxalic acid causes higher rates. We're assuming he collected all his data correctly, right? Thus, the data supports his hypothesis. State whether the SAM can claim that the results are reproducible. No, as all the experiments were done under the same conditions. And or it's only been done once. Outline any further evidence that would be required before Sam could claim that this new experimental design was a valid way of determining the concentration of an oxalic acid solution. Um, I'd say something like data from another group. So basically I'd say data from like a repetition or something like that. A valid way of determining the concentration of an oxalic acid solution. Oh, you'd need to know the data compared to a standard solution of accurately known concentration to determine the accuracy of the technique. Basically, it's not valid if it's inaccurate. You could say something about presence about systematic errors here if you want. You could also say something about systematic errors a bit higher up as well. Hydrogen can help tackle various critical energy challenges. It offers ways to decarbonize a range of sectors. Can be extracted from stuff to meet the decarbonisation target. Global carbon dioxide emissions need to be reduced by 45% by 2030 and reach net zero by 2050. The Australian Renewable Energy ARENA is a cool acronym. Proposes to establish hydrogen hubs to be built in the industries. Okay. Oh. Oh. Ew, a 6-mark question. Write the equation for an overall reaction that occurs in this PEM electrolyzer. Okay, this one's just going to make hydrogen and oxygen. Explain why the hydrogen produced will be considered green. Okay. So I probably want to define green. Green hydrogen is made without producing greenhouse gases. Electrolysis using renewable energy does not produce greenhouse gases. So this process, this H2 is green. Ooh, it does talk about the sustainability goals. Using a relevant sustainable development goal that applies to the use of the green hydrogen in the system, explain how hydrogen hubs could support the sustainable development goal. Okay, interesting. So I'd be thinking we could either go sustainable cities and communities. We could probably talk about climate action, industry innovation and infrastructure. You could talk about the clean energy thing here as well. So I'd say something like climate action greatly reduces carbon emissions from transport or something like that. I'd probably just discuss that a bit more, but I also need to go home at some point. Suggests two sustainability challenges presented by the use of water as a feedstock in terms of United Nations Sustainable Development Goal 6, so clean water and sanitation. So water that might otherwise be used for drinking is used up by electrolysis. Suggests two sustainability challenges presented by the use of water as a feedstock. Sustainability challenges. So requiring access to fresh water is an issue, but I don't think that's really a sustainability challenge. So there's a problem that the problem is just that you run out of water. So the industrial process of collecting water might contaminate it. You could also just extend the first one and then talk about animals, plants, the environment, etc., in the sense that they don't have that. You could also say that you're taking away water so that might otherwise be used for agriculture, so therefore you don't have enough water for doing other things there. Yeah. You could also say something about might need pure water, and then you need electricity and other chemicals to purify it. That would probably be one of the big ones as well. Again, I don't know whether they're classifying that as a sustainability challenge in the sense that I'd want to be just putting water into this. I don't want to be putting other chemicals in with it, so I'd want to purify the water first. You could say that the purification process, like flocculation or whatever, is going to require the use of other chemicals, so therefore, if those chemicals are unsustainable, then the overall process is unsustainable because of that. One possible limitation of the widespread introduction of green hydrogen into society. Safety is one thing. So storage would probably be my biggest thing. Is politics an answer? It's a limitation. Storage can be dangerous. H2 gas has a low energy density. In kilojoules liter, so must be stored under pressure or at low temperatures. H2 is also flammable. So must be stored in, I'll say something like resilient containers. Now I need to go in a second. Hydrogen is a feedstock for ammonia. Ammonia is almost exclusively made by the Haber-Bosch process. Even with energy optimization in place, this one chemical process accounts for, yep. Monash Uni researchers, how much did they pay them to get on this paper, have recently developed a fuel cell that provides an electrochemical synthesis route to produce ammonia at room temperature and slightly above atmospheric pressure. Representation of this process is below. They say recently. This is published in 2011. In this fuel cell, hydrogen reacts at the anode to form H plus ions that are carried across to the cathode by a phosphorus-based compound. At the cathode, nitrogen reacts with lithium ions to form a lithium nitride. The intermediate then reacts with the hydrogen H plus to form ammonia and the original lithium ions. The overall reaction is shown below. Evaluate whether electrochemical synthesis of ammonia provides a potentially more sustainable method for industry to meet society's needs than the equilibrium-based process. Okay. So this is 6 marks. Wow, that's a big new question, that's there. I mean, they've done 5 before, so I guess that's pretty close. I'm just going to throw out what I'm going to say. I've got 26 minutes left on the clock, so I'm just going to throw it out. I could write it down, but the reaction conditions, so you basically say it operates at a lower temperature, it operates at a lower pressure. Do they tell you what? So the lower temperature will mean that there's a higher yield. The lower pressure will mean that there's a lower yield. However, you could say it costs, now in terms of sustainability, so the yield, there's going to be ups and downs from the yield there. You could say that the it's going to use less electricity in the process, or potentially less electricity in the process, because are they saying that? I think it's saying that it creates electricity rather than uses it. I'd have to look at it. As in, it is saying it's a fuel cell. Um, hmm. So you could basically say that there's less electricity, so so therefore less greenhouse gas is going to be produced, making the electricity to run the process in the first place. Um, you could say it doesn't need to use the porous iron catalyst anymore, so therefore it's going to be more sustainable um, because of that, in terms of potentially thinking about the prevention of wastes. Um, Now you do have to use other phosphorus-based things, and the sustainability is going to be determined by the sustainability there. The optimization of equilibrium reactions for both yield and rate in the equilibrium-based process. Yeah, so that was basically what I said before, where you can do it at a lower temperature and that'll give you a high yield there. But the high pressure, the fact that it's a lower pressure might give a lower yield. Again, that's a different process, so it's a bit difficult to actually evaluate it. Again, a weird question. Other relevant ones here would just be designed for energy efficiency. Like we said, it uses less energy there. You could say it's catalysis in the sense that there's a different kind of catalyst thing being used there, because the lithium ions come back, so the lithium thing is basically acting as kind of a catalyst for here. Yeah, and then I talk about prevention of waste in terms of the different waste that you potentially have at the end there. So I'd write that down. I'd probably spend 10 minutes on that, and then that would give me 15 minutes to go back over the rest of the exam. So maybe I'll write out my actual answer to that at some point. But hopefully that was useful for something, and someone watches this. Leave me a comment below or talk to me in class if you've got a question. All right, see you later.